Number 1 asks us for each of the graphs below, we're going to provide the domain, the range. We're going to shade any portions of the graph that are increasing green, any portions that are decreasing red, and then any portions that are constant blue. So let's look at the domain. So on this first one, and these ones really should have arrows continuing on here. And so this one has an arrow this way and this way. We've got kind of these arrows. The graph just doesn't show that. So just in case there was any question of that, I'm just going to get those on here right now. So in this first one, when we're talking about the domain, we have no breaks in this graph. So this blue part doesn't have any breaks, and it has an arrow to the left and it has an arrow to the right. So your domain is going to be negative infinity to infinity. The range is going to be where the y values are. So when we're looking at range, we're looking at kind of up to down versus domain is left to right with the x values. So when we're looking down to up, we see that there's no graph down here, and the graph starts here and goes up. And so the graph is starting at a y value of 3, and it's going up to infinity. And 3 is included in our graph. So we'll have that hard bracket 3 up to infinity for the range. Then it wanted us to do increasing intervals as green. And remember, you read a graph from left to right. So this is the part that's increasing. And you can shade it on the graph like that, or you can draw you can kind of shade the whole thing, which I'll show you here. So this is our part that's increasing. And then it wanted any parts that are decreasing to be red. And so our decreasing is going to be everywhere here. We're decreasing up until this point. And then our constant, it wanted in blue, and that's going to be this middle part where the line is flat. So that's our decreasing, constant, and increasing shading. And then if we were to write out the intervals for that, so our increasing interval is from this x value on, and this x value is 2. So our increasing interval is 2 to infinity. Our decreasing interval, it's decreasing from way down here all the way to this value. And so all the way to the left is negative infinity, and it's decreasing until -1. And then the constant intervals, that middle set of x values from here to here is -1 to 2. For this second graph, the domain, we can see that there's some breaks in the domain. So we see that these blue branches are kind of broken apart. And so we see this first break at this first vertical asymptote, which is at -2. And then we see another break here at +2. So if we're naming the domain intervals, remember we're looking left to right. So we have everything from here up until this value. Then we're going to go here to here, and then we're going to go here forever. So we're at negative infinity up until -2. -2 is not included. Then we go from -2 to 2. Neither of those are included. And then we go from 2 to infinity. The range, when we look at the range, we see a break in the range here. So we see a break here at 1. And now technically we also don't have anything really from here to here in the range. So we would want to figure out really like this number here, or this ordered pair here looks like it's at about 0, 1. So we really seem to have range up until 1. So we go from negative infinity to a y value of 1. And 1 is included, so we'll do a hard bracket there. Then we have nothing until we get to this horizontal asymptote. Oh, and that's not 1, that's 0.5, because this is counting by twos, or by halves. So this is really an ordered pair of 0.5 for the y value. So this is going to go to 0.5. And then this horizontal intercept is at y equals 1. And so we're never going to touch that. These branches just get closer and closer and closer to it, but they never touch it. So we're going to have a soft 1. And then this keeps going y values up until infinity. So we've got from negative infinity to 0.5, and then from 1 to infinity, that 0.5 is included, but the 1 is not. Then if we look at increasing and decreasing and constant intervals, so the increasing intervals, we have, again, remember, read left to right. So this graph is increasing here, and then we hit the vertical asymptote, and then it's increasing from here to here. So technically that's two different intervals when you name it. So then we'd be increasing from negative infinity up until that first asymptote of -2. And then we'd also be increasing from -2 to 0. So we're naming this chunk, and then we're naming this chunk. Then you're decreasing next. So we're decreasing on this interval from here to the vertical asymptote again. And then after the vertical asymptote, we're also decreasing, but we name those in two different chunks because of the asymptote. So we're going to name this set of x values, which is 0 to 2, and then this set of x values, which is 2 to infinity. And then there is no constants in this function, so we put none here. Next graph, we again see that there are no breaks in this blue graph, so we can see that it just continues everywhere, so it's a continuous function. We see an arrow to the left and we see an arrow to the right, so the domain is going to be negative infinity to infinity. And then for the range, we see an arrow down and we see an arrow up, again with no breaks. So then this range is going to be negative infinity to infinity. Then for increasing, decreasing, constant intervals, we are increasing. For this first one, as we read it left to right, we see that we're increasing to this value. And these ones are labeled for us to help us name the intervals. So this was from negative infinity up until this x value. So not quite at -2, just a little bit past that. So this is going from negative infinity to negative 1.86. And then we're going to have another increasing interval from this minimum for the rest of the graph. And so then again, we can see this x value here is where it starts. So it's starting to increase at 0.535, and this is going from there to infinity that it's increasing for those x values. Then in between there, we're decreasing. So the function is going down as we look at it left to right between the min and the max. So then when you name that interval, you'll use those x values from the max to the min. So it starts decreasing at negative 1.86 up until 0.535, where it starts increasing again. And then this one also has no constant area. Okay, so no flat parts. Number 2, determine whether each of the following graphs and or expressions represents a y as a function of x, and then explain your reasoning. So in these equations, remember the thing that we're looking for is if the y value or the y variable has an even exponent. If it has an even exponent, or we see a plus or a minus in the function or in the expression, then it's not a function. So this one is not a function. And you can just say because y has an exponent of 2, or like an even exponent, or you could say that you'll get multiple outputs. So what happens if you have an even exponent is you just end up with multiple outputs for each x value, and we can't have that. And so part B is fine because we don't see any exponents, even exponents on the y. So every input will get you one output. Then once we go into functions into graphs of them, then they have to pass the vertical line test, which means they can't touch a vertical line more than once anywhere. And so if we kind of look at moving this vertical line across, it's fine here, but right here the graph goes vertical. And so then this one is not a function, and because it doesn't pass the vertical line test. So we've got multiple y values for an x of 0, right? So if you just thought about this ordered pair right here is 0, -1. This ordered pair right here is 0, 0. And this one right here is 0, 1. So for an x value of 0, we're getting back multiple different y coordinates, and that can't happen. So then in this next one, if we take a vertical line and we run it across the graph, it never touches more than once. So then this one is fine. So this one is a function. And then this last one, again, also a function. Okay, doesn't cross this vertical line more than once. It gets pretty close to vertical right here, right? Because of this asymptote, but it never crosses the vertical line more than once. So then this one is a function as well. Number 3, for each graph, plot the approximate points of inflection, shade any portions of the graph that are concave up, green, and any portions of the graph that are concave down, red. So inflection points, remember, are right in between the min and the max. Okay, so they're going to be right in between the mins and the maxes, and that's where it flips from being concave up to concave down. So you just want to look between these 2 points here, okay, and the point of inflection is going to be right in the middle of those. Okay, so approximate point of inflection is going to be right between those, so maybe about right here. And then same for over here, we've got about maybe here, here, here. So just about halfway between those mins and maxes. Then it wants us to shade the graph that's concave up, green. So I probably shouldn't have used that color for the inflection points. Let me change that. So here's the inflection points. Okay, so concave up will do green. And remember, concave up is like a smile, okay? So that's going to go from, and let me make this larger here. So that's going to be going all the way to the point of inflection. So that part is concave up. And then this next part at the point of inflection then switches to concave down. So we can see it's upside down, and that's going to be for the remainder of that graph. So in this next one, again, up is like a smile. So we go from inflection points. So between the inflection points there. And then we see this part here, and it just keeps going forever because it doesn't hit another, it doesn't flip to another maximum or minimum. So this one's just going to keep going. And then those other 2 parts are down. So down like a frown, right? So down is going to be upside down like that. And I guess the eyes of this wouldn't be underneath it, right? But so down like a frown. But so then those are the concave down. So label the inflection points and then shade between them for your concave up, concave down. Number 4, given these functions, perform the operations listed. Okay, so now you want to look at each function. We've got f, g, and h. So part A asks us for f of -4. So we're going to take this f function, and where I see x, I'm going to put a parenthesis. and we're going to plug in that -4. So -4 squared is 16, -3 times -4 is +12, and then we have +2. So 16 plus 12 is 28, plus 2 is 30. So this equals 30. Then this next one asks us to plug into the g function. So I'm going to take the g function, and where I see an x, I'm going to put a parenthesis because now we're going to change it from an x input to something else. So now we're plugging in a -3. And so we can just combine these insides. So -3 plus 7 is 4, and then the square root of 4 is 2. Part C asks us to plug into h. And so this one is the absolute value of 3 times your x coordinate. In this case, we're plugging in -2. So then 3 times -2 is -6, and the absolute value of -6 is +6. Part D asks us to plug into 2 functions. And so the first one that we're going to plug into is the f function. So we're going to be doing -1 squared minus 3 times -1 plus 2 for that f part. So -1 squared is 1, -3 times 1 is +3, and then we have +2. 1 plus 3 is 4, plus 2 is 6. So that's our first part. Okay, then we're going to add in the g function. And the g function, it asks us to evaluate at 7. So g is this square root one, right? So for the g function, and I'm just going to write it up here, we're going to be doing the square root of 7 plus 7. So we're plugging in 7, right? And 7 plus 7 is 14. So this is the square root of 14. And so I would just leave your final answer as 6 plus the square root of 14. You can do the decimal if you want to, so you can type it in your calculator, but you don't have to. You can just leave it like that if you want to. E asks us to plug -5x into the f function. So remember, we're going to have something squared minus 3 times that thing plus 2. And the thing that we're plugging in is the -5x. So -5x squared is +25x squared. -3 times -5x is +15x. And then we have the +2. And then that can't be simplified any further. So that would be our final answer there. Then this next one asks us to plug into g. And so g is the square root of x plus 7. And now we're plugging in 3x minus 2 for x. So then we can simplify underneath that root any like terms, and these parentheses don't matter because there's nothing out front of it and there's nothing behind it. So we don't actually need these parentheses. So when you're thinking about combining your like terms, you can just combine the -2 and the 7. So we've got 3x, and then -2 and +7 is a +5. So then your final answer would be the square root of 3x plus 5, and you can't simplify that any further. G asks us to plug -x into the f function. So we'll have something squared minus 3 times something plus 2. And that something that we're putting in is -x. -x squared is +x squared. -3 times -x is +3x, and then we have the +2. And then no like terms there, so we'd be done. And then this last one asks us to do 2 functions again, so we're going to plug 2 into the g function. Okay, so we're going to have 2 plus 7. So then that's square root of 9, which is just 3. Then we're going to plug into the h function. And the h function is the absolute value of 3 times x, which in this case is -8. So here we have the absolute value of -24, which is just positive 24. And then this problem asked us to subtract these two. So 3 minus 24 is negative 21 for our final answer for that one. Number 5, use a grapher to determine all local minimum, maxima, or minima for the function below. So let me just write out the steps that you're going to do in your calculator for this. So remember, you're going to hit the button second, and then you're going to hit trace. And then you're going to select either minimum or you're going to select maximum. Then it's going to ask you to be on the left side of your minimum. So you'll get to the left side and then hit enter. You'll get to the right side of your min or max and hit enter. And then hit enter again, and it'll give you your exact, your decimal version of your min or your max. Okay, so then I just did them in decimal so I can get screenshots for you so we can see them. So this is the first one. And so if you used your calculator correctly, this is the minimum you should have come up with, okay? So there isn't a max, okay? And this is our minimum. So our minimum value is negative 1.083 when x equals 0.0833. So that's for that first one, okay? That's our minimum. Then for this second function, okay, we have a min and a max. So our maximum is here, okay, at a y value of 1.262 when the x value is 0.548 or 9. So I'm going to round up since it was 8.5. Then the minimum is here. So the minimum is negative 4.225 when the x value is negative 1.215. And then the final one looks like this. And so we just have a maximum again. So no minimum for this one. And the maximum is at negative 4 when the x value is 5. So just be sure you actually follow the calculator steps, second trace, min or max, because otherwise these decimals will be off. So I'll know that you didn't use your calculator correctly. So make sure you know how to do that. All right, then number 6 asks for boundedness. So upper boundary, lower boundary, or both. And so in this first one, we have a boundary below. So this one is said to be bounded below because there's a line that it's not crossing underneath it. It's going forever up, so there's no upper boundary. And this lower boundary is at a y value of 0. This next one is a little bit hard because it looks like it has it doesn't like label the horizontal asymptotes, but there are some horizontal asymptotes here and here, which I probably should have put on the graph. And so this one is actually bounded above, okay, at 2. And it's bounded below at y equals negative 2. And then this next one is also bounded. So we see this upper boundary. We see that the circle doesn't go above that. And we see that the circle doesn't go below this. So this one is also bounded above at 5 and below at negative 1. Number 7, determine if the function is even, odd, or neither. So remember, you can certainly graph this in your calculator to find out. If it's symmetric over the y-axis, okay, so if it's symmetric over the y, then it's even. Okay, and if it's 180-degree symmetry around the origin, which is 0, 0, then it's odd. So you would just graph it, draw a sketch, and say one of those. You would say even because it reflects over the y-axis, or you'd say odd because there's 180-degree symmetry around the origin, or you'd say neither. I'm going to do it algebraically by plugging in negative x. Okay, so I'm going to look at plugging in negative x. So I'm going to take this function, and where I see x, I'm going to put in the opposite of x. So then negative x squared is positive x squared. And then negative 4 times x squared is just negative 4x squared. And we still have this plus 3. And we can see that this first term is the same and this last term is the same. And so then if the terms are the same, then it's even. Okay, because that means that f of negative x equals the original function f of x, and that means even. For this next one, we would take negative x squared, and we would do 4 times negative x. Negative x squared is positive x squared. And then negative 4 times negative x is negative 4x. So then we see that this first term is the same, but this next term is opposite. So it's a combination of the same and opposite. So this is neither, because f of negative x isn't the same function, and it's also not the opposite function. Next one, so we'll do g of negative x. So we'll be doing 2 times negative x cubed minus 3 times negative x. And when we bring a negative to an odd power, it will stay negative. So we have negative x cubed here. And then negative 3 times negative x is positive 3x. 2 times negative x cubed is negative 2x cubed. And so then when we look at these terms, we'll see that this first term went from positive to negative, and we'll see that this second term went from negative to positive, so they're opposites. So g of negative x is equal to the opposite of the original function, and so then this means odd. And then this last one, when we plug in negative x, so we have a negative out front. Okay, so we have negative x cubed. So we have negative times that negative x to the third, and then plus 13. And so a negative cubed is going to be a negative. So we have a negative x cubed plus 13. And negative times negative x cubed is positive x cubed plus 13. So then we see that this first term is opposite, and we see that this second term stayed the same. So this is going to be neither. And then number 8 asks us to do a bunch of things: determine domain, discontinuities, classify them, find vertical asymptotes, horizontal asymptotes, and then look at end behavior. So remember that the things that we're looking for when we're looking for domain is, do we see division or a square root? Okay, if we do, then there's possibilities of issues. If we don't, then it's all real number domain. So in this first one, we see the bottom here at x squared minus 9 is going to be a problem. So anytime that x squared minus 9 equals 0, we'll have an issue in the domain. So anytime that x squared equals 9, if I added 9 to both sides, so this means plus or minus 3 is going to be a problem for this domain. Okay, if we plug in 3 or negative 3 into the denominator, it will give us 0. So now we want to write out the domain. So I'm just going to get rid of that so I can write out the domain. this means that everything leading up to -3 is fine. So -infinity to -3. And then everything from -3 to 3 is fine. And then everything from 3 to infinity is fine. So everything except 3 and -3. This is because 3 and -3 are both discontinuities. So now you check if we plug these into the top part of our function. Okay, so if we plug them into the top, do they make the top equal 0? Well, they're not going to because there's nothing to plug them into. There's no x up here. So the top is always 4. So that means that both of these are infinite because they only make the bottom 0, which makes them vertical asymptotes. So our vertical asymptotes are x equals 3 and -3. Then for horizontal asymptotes, remember that you look at the degree on the top and bottom. So in this case, our degree on top is 0 because we don't have an x term. So it's x to the 0 and we have an x squared. So our top is smaller. Okay, our top degree is smaller. That means that it's automatically a y equals 0 horizontal asymptote. And that means that our end behavior is going to go towards the asymptote at both ends. Okay, so as x approaches -infinity, it's at 0, and as x approaches infinity, it's at 0. And you can certainly graph this. I don't know exactly what it's going to look like, but it has a vertical asymptote at 3 and -3. So it's going to look something like this. I don't know if the branches are in the right spot here, but it's going to look like this. So at these ends, it's going towards 0. We don't care what it's doing in the middle, but the ends go towards the horizontal asymptote. All right, then the second one has a square root. So what we can't do in math is have this number be less than 0. So off to the side, I'm just going to solve this so that x is, or that number under there is greater than or equal to 0. So I'm going to subtract 12 from both sides. And then I'm going to divide by -3. When I divide by -3, I flip this symbol. Okay, I flip the inequality anytime I multiply or divide by a negative. So we want x's that are less than or equal to 4. So here's 4. We want any number less than or equal to 4. So that means that our domain is -infinity up until 4, and it can include 4, so that's a hard bracket. Okay, there aren't any discontinuities here. Okay, this graph just isn't fully continuous. If you graphed it, it would look something like this. But it doesn't just break and start over. So there aren't any discontinuities. These are going to be problems in the denominator. Okay, discontinuities are in the bottom. We don't have a bottom number here. So then we don't have any vertical asymptotes, and we also don't have any horizontal asymptotes. Now the end behavior on this, okay, so if we graph it or we look at this graph, okay, so again, this is kind of what this graph looks like. It's not doing anything on the right side. Okay, so there's nothing happening on the right side. And on the left side, it's just going unbounded up. It's just going to keep going up and up and up as you continue to the left. So as x approaches -infinity, your graph is going up. Next one has a denominator. Okay, so we've got two problems in this domain, +3 and -2. So if you think of solving each of these off to the side, we would subtract 2 from both sides, right? And then x minus 3 equals 0, we would add 3 to both sides. So these are our problems. So -2 is an issue and 3 is an issue. Everything else is good. So everything down here, everything in between, and everything up here. So -infinity up to -2 is fine. -2 up to 3 is fine. And then 3 to infinity is fine. But make sure you have soft brackets because we don't want to include those numbers. Then those two values that make the denominator 0 are our discontinuities. So x equals -2 is going to be a discontinuity, and x equals 3 is going to be a discontinuity. Well, we can see that there's an x plus 2 factor in both of these. This means that this -2 will make the top 0 as well. That makes it a removable discontinuity, meaning there's going to be a hole. 3 only makes the denominator 0, so this is an infinite discontinuity because it's a vertical asymptote. So x equals 3 is our vertical asymptote. X equals -2 is going to give us a hole. Then when we look at the horizontal asymptote, okay, this is a degree 1 on the top. We only have x. Down here, we're going to have x times x, which gives us an x squared. So our top degree is again smaller because it's a degree 1 on top and a degree 2 on bottom. So that means our horizontal asymptote is going to be at 0, which means both ends of this graph will go towards 0. So as x approaches -infinity, it's at 0, and positive infinity, it's at 0. Then our final one here is just a linear function. And so this is going to have a full domain. It doesn't have any issues because it doesn't have division or a square root, right? It just looks like this. So there's going to be no discontinuities, and there's going to be no asymptotes of any kind, vertical or horizontal. So then we just got to think of the end behavior. So on the left side, this is going down. So this is going to -infinity. And then on the right side, it's going up. So that's going to positive infinity.